Raspberry Pi that we used, but you'll get the idea. So the magic trick that I wanted to perform is a simple trick like that, like moving objects with your mind. So first we recorded just the background because I thought that may be useful, and then turned out actually it was not necessary, but then we run the magic trick. So you have an object on the table, and then with your mind you can make it move left and right. Now it's very easy to see what the trick actually is, how that works, right? Because what do? Why does the jar roll left to the right there? If we just do it like that, unfiltered, then it's not a cool magic trick at all, because you can see it's just lifting the table, right? So obviously it's going to roll to the side that is lower. So that won't be very convincing. Now, some magicians do that. If it's dark enough, you can get away with it. If your table has a black cloth and the background is all black, people may not be able to see that you actually shift the table. But I wanted to do it slightly differently, a bit more elaborate if you want to. I didn't use the jar, but we used a hexapod robot. We had implemented wrench estimation on the hexapod robot, which means that if you could put your finger on the robot and then just push a little bit, and it will go in this direction. So if I tilt the table, then also a force is acting on the robot, and it's going to follow the direction of the force. So that worked, but I still have to lift the table to do that. So I implemented luckily that particular year, the magic competition was not in person, but it was done virtually, right? It was online. So I implemented a program that would capture the real-time video stream. Then in real time, it would simply adjust the angle of the table so that the table was always flat. So even if you move the table like this, in the video, the table will look flat. Right? And then that's a whole new level. Then the trick is actually kind of cool. Because then I could just go like this, and the robot would move, and the jar would move with it. So the tricky part was to figure out where the edge of the table is, what the angle of the table is, and then simply to rotate the image so that the table is always flat. Right? And then if I moved like this, if I realign it, then my body would move a little bit. So it would move a little as if I'm moving a little bit like that. But that bit wasn't too distracting. And so the question is, how did we implement that? Let me see. So we want to show the ability to move objects with our mind as a simple demonstration. But if you look at it, then of course you can see the table move, which means you know exactly how the trick works. But since the competition is virtual, I can record the video from the webcam, and then I can apply a processing step to always align the table and then stream it via Discord. So we ran that particular application in front of OBS Studio. Then OBS Studio would broadcast the video. And I need to be able to run that in real time, of course, because otherwise people would notice that my speaking, the video of my mouse moving, and the audio that they hear is out of sync. Right? So you cannot do too much processing. So then I tried many different I tried 3 different approaches. First one was background subtraction, and we'll be looking at that particular algorithm later on using the mean shift algorithm. And then the idea was that I extract what's in the background, then what's in the foreground is the part that I'm interested in, and then I just rotate that part, make sure that this doesn't change. I come up with the best rotation angle in order to minimize the change in that. That would also be difficult with images where not a lot of things are moving, because then eventually they would blend into the background. So if I sit down, do the trick right away, that's okay, but then the algorithm would update the background, so then if I have to do it again 3 minutes later, it wouldn't work anymore, because the other parts are now part of the background, so they won't move anymore, because they haven't changed for such a long time. And also, anytime you're doing this kind of background subtraction idea, changes in the image, then shadows are a problem, because if I move my hand, then even though I move the hand on top of the table, or like this, then the shadow behind is also going to move. So then some part of this is going to be part of the foreground, which will also be rotated then. So that didn't work so well. Another algorithm that, or idea that is commonly used for that kind of application would be to register the image using more complex features, like ORT features, and we'll be talking about ORT features in the future too. Those find special points of interest in the image, but in the video that we had, the most interesting points were on the garbage can, which is not actually part of the table. So then, since the garbage can doesn't move, it would basically assume that the best thing to do would be not to rotate the image, which means that the table, you will see the rotation of the table very easily. But what worked best is, another approach is to calculate the optical flow, which is basically looking at how things are changing in the image, and then make sure that you regularize that, make it constant. For things up and down vectors on the left and right, and then figure out how much the rotation was by how much the edge of the table moved up and down. But that was too slow for real time on a Raspberry Pi. It didn't run fast enough, even though I think I probably could have gotten that to work if I had more powerful CPU. So what I ended up doing in the end was to just do exactly this template matching. So I took a picture or area of the left side of the table and the right side of the table. Right? Then, even though I rotated it, the picture would slightly change, but that didn't really matter because the maximum hits were still on the right and the left side of the table. Once I have the right and the left side of the table, then I can calculate the angle of the table. Then I would rotate the entire image so that the table is always stable. So then, when you look at the image, then the table would be always exactly flat. I could move it by like 10, 20 degrees, and then it would just look like I'm doing a lot of shaking here. But the table was like rock solid flat, and the thing would move on top of the table without any inclination. And of course, when you do the trick, you don't need that many degrees of freedom and that many degrees. You just need like 5, 2, 3, 5 degrees, something like that. And then the thing is going to roll, or the robot is going to start moving. So that was pretty interesting. What was even more interesting was the fact that for the magic competition, for the magic show competition, the judges consist of 2 groups of people. One are engineers, computer scientists, AI researchers. The other one is a group of professional magicians. So people that do magic professionally or semi-professionally, quite serious magicians. And the engineers thought it was pretty cool to use template matching, simple algorithm solves the problem, all nice and good. But the magicians were extremely upset about this. They didn't like this at all because they said it is actually a taboo to change the video stream. So that's not something they would do. Similarly to taboo would be, taboo in magic is to use a plan. So of course, if I have a magic trick and I ask you, here I have 3 pens, right? Now take the 3 pens, put them behind your back, and then pick one of them. Yeah, I look away. No, I mean, you have 3 pens. I look away, right? And now pick 1 pen. Let me know when you picked it. You have the pen?
Oh, yeah.
Yeah, think about the pen. Send the pen to me. Red. Blue, right? So if I get the correct color, that would be amazing, right? It would be much less amazing if I give you 50 NTD and tell you pick the blue one, right? Then this would be, it would look like an amazing trick, but in fact it only works because we know each other from beforehand, and I know which one you're going to pick, right? Or if you think that's too easy, then we can have a more elaborate scheme, right? So we could have like, oh, on Monday you pick the red one, and on Tuesday you pick the blue one, and on Wednesday you pick the green one, or something like that. Then any day of the week we do this trick, I would know which one you're going to pick. Or, like a lot of the mind reading things is with somebody running around, and then I ask you, have you picked the pen yet? And then you may say, if you pick the red one, right, you say, yes, I'm done. If you pick the blue one, you say, oh, hold on a second. Oh, yeah, now I'm done. And if you pick the green one, you say, yep, sure, I'm done. Right? Then I also know. But all of these will look to the audience pretty impressive, right? Because we get the pens 100% of the time. But really, there's no skill involved. It's only the fact that we know each other and we can come up. So this is what's called a plan. And this is a taboo in magic. Like, no real magician would do that. Because if you allow for that possibility, then of course all magic tricks become trivial. Anything with the volunteer, if the volunteer is working for you, then of course you can do amazing things, right? Like, think of a number between 1 and 10 billion, and I can guess what number it is if I know that you're always going to pick 152. So what's funny is that they were very upset about me processing the video, and they said, oh, no, you can't do that. That's a taboo. Like, that's not fair. Right? That's basically like doing unfair magic. The thing that I don't understand about this is that they had another magician, and that magician was doing the same trick, except he, instead of processing the video, instead of altering the video, he was time delaying it. So he recorded the video 1 minute before and then was playing it a minute afterwards. And then the trick was basically that he would tell the volunteer to turn around and hold up your fingers like 1, 2, 3, 4, 5 in the air. Yeah. No. So like 3, right? And then what would happen in the video is that he would go 3, and now your hand comes up and goes 3, right? And then I go down, then I go 2, then your hand goes down, then you go 2, right? But the fact is, he actually was moving first, right? But because your video stream is delayed, I can just see, I just tell you, okay, whenever you feel like it, move your hand up. Then you move your hand up with some numbers, like that, and then I go afterwards, right? Then that's much easier, right? So that trick worked by delaying the video for 30 seconds, right? Because your video was running 30 seconds after my video. And that's why it looks like I moved first, but actually he moved first. That was okay. The magicians all thought that was perfectly legal. But to actually rotate the image, that was not acceptable. And then I think like, because, I mean, there's probably a reason, but I'm like, okay, but this doesn't seem fair. Like, if I can delay the video, why can't I rotate the video? It seems pretty arbitrary distinctions that they have with respect to the ethics of magicians. But of course, I'm not going to argue with them. They are the ones that are trying to do this professionally and make money with it. So I don't want to be on their bad side. I understand they probably have a reason for it. Why time delay is okay, but rotation is not. So anyway, this template matching is quite useful if you're looking for well-defined shapes in an image. It runs extremely quickly. Even on a Raspberry Pi, you can do this on a pretty large image. Then rotate the image, and then convince people that you have amazing magic powers. So it was quite a fun project to do, especially with the Scarab robot. So now let's have a look at more details. I'm going to continue with these slides next time, but I want to do the edge detection first today before we continue. Actually, no, I just continue with this. So here we have 2 other masks that we can apply. Let's have a look at the second one. The second one is just a whole bunch of ones. So if I apply that to the image and then scale it, because now now I would be out of range, right? If I have a pixel with a value of 255, it would be, if I apply this mask and there's a bunch of white pixels, it's going to have a final value that's above 255. So then I would need to divide it by, in this case, 25. In order to make sure that the brightness is not changed, or I need to normalize it in some form. What will be the effect of that mask on the image? As you may guess from the name, it actually blurs the image, but why does it blur the image? What actually happens with this particular map? Well, if I take that image and then divide it by that mask, apply it to the image, then divide it by 25, then that means every pixel is going to be replaced by the average of the pixels in its neighborhood. Because we get 1 times this neighbor plus 1 times this neighbor, so we sum up all the neighboring pixels and then divide it in order to scale it to be within range. So now I have the average of all the pixels in my neighborhood, which means that things like edges are now going to be blurred out. They're going to be, if there was a sharp contrast before between 2 pixels, now it's going to be flattened out. It's going to be much less apparent, which means that edges become much softer. We now blur the edges. And then here, this is the output of a blurred image. Everything much more fuzzy, much fuzzy. Sorry, this is a sharp image. This is a blurred image. You can see the police and everything. The features are all washed out. Now the other mask is an interesting one because it takes the difference between the pixel and its neighbors and then enhances it, makes it larger, multiplies it by a factor. Because that's the difference between this pixel and that pixel, the difference between this pixel and that pixel, difference between those two, all of those added together and then multiplied by a slightly larger factor. Instead of 4, which is what it should be, we multiply by 5, which means that now that the difference is in half, increased. So now we make the edges sharper. So here now this is sharpened. Also, because the response of that particular filter can be positive or negative, and I just scaled it to be within range. That means that the average brightness of the background now increased. So here, this is all average gray now as opposed to darker. So here we have another picture. So here's an input image from Taiwan, and of course humans are very good when it comes to recognizing shapes and things like that. So things like that, this would be enough to give you an idea that this should be a cow, right? No color necessary. Only the outline of the shape would be sufficient to show colors. and even what type of car it is, usually quite. And even if it doesn't really look like a real car, we still understand that this is a car. Which is why it's really hard to do computer vision to get that kind of image. 139,500 images of cars. Wow. Somebody did a lot of drawing there. Let me just the slides. So even if we get rid of all the color and all the textures, we can still identify objects very naturally, very easily, based on the outline of the shapes. And the basic assumption there, in order to be able to do that, there has to be some contrast between the object and the background, at least in large parts of it. The edges are changes in the brightness of a pixel and its neighbors, and then the first step in order to detect an outline and register it or match it to something would be to extract the edges and then construct the outline from those edges. So here's some input image, and now we would like to be able to detect the edges in this image to eventually conclude that this is a temple in Taiwan. So when we look at it in more detail for an edge, we sort of expect something like this, a brightness value that's very low, and then a big change, and then it continues on here, and then drops down. So then that will be an edge. But in reality, our edges in the image don't look that crisp. Detecting this would be trivial, but unfortunately it's not that easy. Our edges look more like that. So the change in brightness will be much higher, and then often, even though we may have a solid foreground background color, the edge, the trailing edge may be rather slow rather than exactly this 90-degree split here or 90-degree vertical line going up. So there's a lot of noise when dealing with edges. And this is the brightness value of the image along one row. So here I have a value of 90, and it jumps to 120, and then here it decreases much slower. So we also need to worry about noise. So then this is a lot more interesting. Where are the edges in this particular image? If this is our image function. So it's not so clear what, how to extract this kind of edges from a noisy image. Now, computer vision researchers, for some reason, they like to apply, or they like to use calculus when describing their algorithms. That makes it a little bit, because a lot of students are scared of calculus or don't feel comfortable talking about derivatives and gradients and norms and things like that. I think that doesn't really help understanding in a lot of cases. But as far as computer vision research is concerned, the general description, the way that researchers look at the problem is to say that we have an image function I, which has two parameters, x and y. So it's a two-parameter function, and that represents the image. Now, I, x of y would return the pixel information for that particular location. And this would be things like the gray list level, if it's a gray scale image, or RGB values, or HSV values, or YUV pixel values. Right? Now, fine, they like to do it as a function, but there's some differences between functions and images that are sort of generalized away, and it makes it actually more difficult to incorporate those later on into the analysis. So for one thing, what's the main difference for an image function and a image that we process in our computer? You have to give me back my pen. So even though we talk about the function, mathematically it is a function, it's not the kind of function that you would be familiar with from high school or first year calculus course. Let's say what is this function? If I show it like that, then just for one, then this would be a function of one variable, right? X and Y. And if you needed to guess at what the actual function is, then what would you guess? See, I guess I should, I draw it like this first. How about y is equal to x? Does that match? No, right? Why? Huh? It's a polynomial, right? Y equals x would be a straight line, it would be a linear thing. So probably it's yx squared, right? So now I have a mathematical function that we're used to, but there's a lot of differences between an image and mathematical functions. For one thing, if this is my function, then this also exists, right? But it doesn't really make sense for the image at -5 or -3 or -2. So the domain of functions is quite often from minus infinity to infinity. But for an image, it doesn't make sense. The image, the domain of our image is how many pixels we have in the x direction. The other thing is, the other difference is that I can ask for y is equal to 1 squared, which would be 1, right? Y is equal for 2 squared would be 4, right? But I can also ask for y is equal to 1.5 squared. Or y is equal to 1.5000000001. So the functions are usually continuous, or they are continuous. But that doesn't make sense for our image, because our image, I have a discretized version of this. I only know 1 and 2 and 3 and 4 and 5 and 6 and 7. So really our function just looks like that. The data that we have is just these points. And I can have a guess about what it looks like in between, but there's no way that I can actually read that out. So when we're dealing with this image function, then yes, mathematically it's a function, but it's not the kind of function that we traditionally use in calculus. And by using the language of mathematics in order to describe our algorithm, we're actually abstracting away a lot of the information that is really necessary, that is really important in order to implement the function. So my view is that it would be, I've come to the conclusion, that it would be a lot better if we used programming pseudo algorithms in order to describe the mathematics of computer vision. Because once you have the algorithm, then every step of it is defined. Now, an edge is defined. We talked about the edge. We said that's a big jump in the intensity between one pixel and its neighbor. So that's a big change in the image function. When you talk about change with respect to a function, then that means you're talking about the derivative. If I have this is my function, then mathematically the change of the function would be the tangent that is applied here, and that would be f of x is equal to this would be f dash of x, right? The first derivative. So then mathematically we define an edge as a pixel where and now since we have a two-parameter input function, we don't have the, we have a multivariate derivative. So we have a derivative with respect to x and a derivative with respect to y. So we need to deal with the partial derivatives in the x and the y direction. So, looking at it mathematically, our edge is defined as some kind of, the most primitive version of defining the edge would be to be a pixel where the first partial derivative in either x or y is above some threshold. If the derivative is larger than something, then that's where we have an edge. Also, Apart from the fact that our domain is limited and that our readings are just discretized, another issue is that we really don't deal with analytical functions. Like it's not like I'm looking at x squared plus sine of x, right? It's the response from the sensor. So the partial derivatives that we can calculate, they don't need to be coherent or consistent in any sense. If there's a white wall and a black wall, then those are going to just change dramatically. There's no way to really predict that. But, okay, let's move along and think of it from a calculus perspective. We need to estimate the partial derivatives for x, which would allow us to detect a edge along the row. So that would be a vertical line if we're trying to detect vertical edges. Then I can estimate the derivative. I cannot analytically solve it because there's no function. All I can do is numerically estimate what the derivative is at that point. Even though they write it like an analytical derivative, it really is not. It's just the numerical approximation of what we can do there. And so that will be the difference between the current pixel and the next pixel. And as we've shown already, that we can easily implement as a convolution with a simple matrix like this. If I want to have a 3 by 3, then I could just have the right neighbor minus myself. That would be the difference between myself and the right neighbor. But that's not particularly nice because now it's sort of weighted to the right. Symmetric, more robust approach, because in that case we're averaging over the left neighbor and the right neighbor, or looking at the difference between the left neighbor and the right neighbor, is to use this particular convolution mask where we have -1, 0, +1 in order to estimate the first derivative along x for this particular pixel here. And that's called the Breivik operator. So there have been, at the beginning of computer vision, there were lots of people proposing different masks. The most common format is actually, or version is the Sobel edge detector, which we will see in the next slide. Now, the problem with this one here is that it basically emphasizes the difference between pixels that are very close to each other, but that means if they are shifted by noise, then there will be a huge difference in the response. So noise will be amplified using the Roberts operator. And it's more stable with respect to noise if you use Breivik, because the two pixels are further apart, so any noise will be sort of averaged out over the bigger distance. Now let me talk about this a little bit more. This is actually one of the important rules in robotics, artificial intelligence, kind of application, computer vision applications. When you look at some system, and you want to track a ball, for example. So the ball that is rolling through the image, like this. Then, one thing that you can try and detect would be the position of the ball. Right? And if you want to track the position of the ball, then that's okay. You can implement an algorithm, you can do that. Other applications where we would have that would be GPS. If you have a GPS coordinate system and you're trying to track a vehicle, if you also are interested in the position, now we can do quite well. Now, as far as difficulty is concerned, if I want to track how fast the ball is moving, right? So if I want to track if the ball, what velocity it's moving at, then what do I need to do? How do I calculate the velocity of the ball as it's moving through the image? Well, then I have to look at the position of the ball at time t, and then the position of the ball at some other time later, t plus delta t, right? Then I need to subtract those two, look at the difference between those two. And subtract them. So, in that case, that's equivalent to calculating the derivative. Now, any noise you have in your system is going to be greatly emphasized. You're going to have a lot harder time getting a good velocity estimate than getting a good position estimate. Now, if I want to calculate the acceleration of the ball, then what do I have to do? So the acceleration is how much the velocity changes, right? Which means I need to calculate the velocity at time t and the velocity at time t plus delta t, then subtract those two, and then be able to estimate what the acceleration is. That is extremely noisy. There's really no way to do that from a standard video feed. Because there's going to be so much noise in your system that it's basically impossible to do that in reality. Similarly, here for GPS. So if we go from here to there, then we're calculating the derivative. And anytime you're trying to do that, you have to be aware of the fact that noise is going to be your biggest enemy. You're going to have a lot of trouble unless you have extremely clean data. It's going to be impossible to do that. On the other hand, if you have velocity information and you want to get position, then you need to integrate. If you integrate, then that's always a good thing because you sum it up of a whole bunch of different readings and then you calculate an average of those. So any kind of noise that you have will be averaged out. So let's say position here, maybe you just want to know if the thing is moving or not. Right? In order to determine if the ball is moving or not, you can average it over a number of frames and then calculate the average of the position at times t and then t plus 30 seconds. You can see if those two averages are different. That will be very, very stable. Very clearly you'll be able to distinguish that, independently of how much noise you have in your system. So in general, when you're dealing with intelligent systems, robotics, AI, computer vision, if you can stick with the integration phase, then that's much, much easier. And try to avoid having to calculate the derivative. So the first derivative, okay, that's possible, right? Usually that's sort of doable. Second derivative, or you're already asking for trouble. If you need that in order to solve your particular application, if you must have the second derivative, then maybe get a different sensor. Maybe add some other sensors to reduce the noise. Calibrate your system more carefully so that you have a better idea of what the noise actually is. So you can estimate variances of the noise and things like that. But if you integrate things, then all is good. And things are going to work pretty well. So now with the Previtt operator, this one is a little bit better, but in order to avoid noise, we can make it slightly better with a 3x3 mask. We can have 3 rows of that and then take the average. So then we're saying that an edge is defined not just in the row that I'm in, but also in the row above and in the row below if there are strong responses in all 3 of those. So that will be the Previtt horizontal operator, and then the Sobel edge detector is basically exactly the same thing, except that instead of having 1s here, we put 2s here. So what that does is it puts slightly more weight on the current row. Right? The current row accounts for 50% of the response of this filter. The top and the bottom only for 25% each. And this will be the Sobel edge detector operator in the horizontal direction, and then the vertical one is just rotated by 90 degrees. Now, these are edges in the vertical direction. Here we recognize edges in the vertical direction. Here we recognize edges in the horizontal direction. Of course, I don't really need to do that. I mean, I'm not limited to just the horizontal and vertical. I can also have a Sobel mask like this, which is on a 5x5 convolution mask, which, when you look at it, is -1, -2, -1, 1, 2, 1. So it's a Sobel mask, but it's skewed by 45 degrees. So this would be an operator that would have a strong response to 45-degree angle lines, if I need to detect those. So we can run that. Now these are called Kirsch masks, and in fact there is 4 of them that we can run. That will give you a maximum response then and a better reading for the 0, 45 degree, 90 degree, minus 45 degree angle. And here's the response of this this operator, and you can see some of the 45 degree angles here are coming back as like this part here in the door frame. This one is roughly a 45 degree angle, and we get a strong response there. And here's the Sobel edge detection for Sobel X in the X direction, Y direction, and then the Kirsch mask for 45 degrees going upwards and then 45 degrees going downwards. And here are the responses on the Taiwan image. So here, very strong response on the columns that are all vertical lines. Here, strong response on the horizontal lines. This one, 45 degrees going up, 45 degrees going down. That is actually, I don't see any. We could have thresholded to see whether. Yeah, maybe try and do that. So here we'll try and make it look a little bit clearer about the response of the filter. So this would be image 10. So let's say this is the maximum, and then set that image. Everything that's within 20% of the maximum, I set to white. Everything else will be black. So let's see what that looks like. So that would be image 10, where image 10 greater than 0.75 times make it white, otherwise black. NP.where. So here's the strongest response. Those two vertical lines here. Let's set our limit a little bit higher. So here you can see we have many horizontal edges. Then take the vertical edges. So, and 13. So here the roof tiles are plus 45-degree angle. Here we have horizontal responses. And show this one. Not so many sloping down, 45-degree angle. This father was calculated. And then just the outlook. How come it's already on the Oh, now it's okay, good. Then that's it for today's class. Next week, we'll be looking at second derivative operators for edge detection.